तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We had a look in the last class at the classical differential equation method of solution of a transient problem. Let us briefly recapitulate the features of solution by this particular method. The solution consists of two parts. One is the complementary function part of the solution. This is obtained after solving the characteristic equation of the system, and the roots of the characteristic equation gives us the natural frequencies or the force free part of the solution of the system, and these natural frequencies are characteristic of the particular system irrespective of the type of excitation. And the complementary part of the solution is also referred to as the free response of the system. This consists of various natural frequencies with coefficients whose values are a priori not known to start with. Then there is the particular integral solution, which consists of frequencies which are present in the excitation or the forcing function. This is also referred to as the forced response of the system. The forced response of the system depends upon not only the parameters of the system, but also the excitation function or the forcing function. Now together the particular integral solution and the complementary solution together determine the total solution of the system, but to evaluate this solution specifically we need to evaluate the arbitrary constants that are present in the complementary part of the solution. To do this we need to know some initial conditions regarding the variables which we have to solve for, and normally this transient solution is calculated based after switching operation, say at t equals 0. Information about the reactive elements in a network, capacitors and inductors, are known to us before the switching operation, let us say at t equals 0 minus. Using this information we assume the continuity of the capacitor voltages and the continuity of inductor currents in the time from t equals 0 minus to t equals 0 plus, assume the same values to hold, and therefore the initial values of the inductor currents at t equals 0 plus and the capacitor voltages at t equals 0 plus are known to us. Using this information we will have to find out the initial values of the response quantity and its various derivatives depending upon the order of the differential equation that is involved, and this particular process involves quite some manipulation, as we have seen in the particular example. Now it sometimes turns out that the assumption that the capacitor voltage is continuous and the inductor current is continuous breaks down because of the nature of the particular circuit. Today we will take up two examples where we cannot assume continuity of an inductor current and a capacitor voltage. So that means the inductor current may jump from t equals 0 minus to t equals 0 plus, and so can a capacitor voltage. We will look at two specific examples of such situations and then move on. So we will talk about special cases of discontinuous inductor currents. Let us take a circuit in which we have a 12 volts DC source is connected to a series combination of 2 inductors and 2 resistors. Let us call this L1, call this L2, 1 Henry and 4 ohms. And let us have a switch which is kept closed for a long time, and the switch is opened at t equals 0. Now, if I call this IL1, the current in this inductor as IL1 and the current in this inductor as IL2. Now, the switch is opened at t equals 0 after it has been closed for a long time. So, let us see the nature of IL1 and IL2. This is the current in the first inductor, this is the current in the second inductor, IL2. Now, when the switch is closed, 12 volts drives a current to the 4 ohm resistor, therefore, there is 3 ampere current because this is a short circuit, and therefore, at t equals 0 minus, this current is 3 amperes. So, whatever may be, it is reaches at 3 amperes here. As far as IL2 is concerned, because this is a shorted, the current passes through the shorted switch avoiding this L2, therefore, it is 0. Current is 0 here. Now, when the switch is opened out, by Kirchhoff's current law, the same current must pass through them. So, there must be a common current which is certainly can't be equal to 3 amperes and 0 amperes at the same time. If continuity is a continuity of current in this inductor will demand that IL1 continues to be 3 amperes, the continuity of the current in the inductor will demand that IL2 continues to be 0 amperes, but both these conditions can't be met because at t equals 0 plus the same current must pass through both. So, we have the situation that IL1 0 minus is 3 amperes, IL2 0 minus is 0 amperes, and we further require that IL1 0 plus must be equal to IL2 0 plus, whatever that is. It certainly cannot be, if it is equal to 3, then the continuity of current in this is violated. If it is equal to 0 amperes, the continuity of the current in the first inductor is violated. Therefore, we must now find out IL1 0 plus and IL2 0 plus. How do we do that? Now, obviously, there must be a jump in current because obviously this cannot continue at 3 amperes at 0 amperes. So, there must be some kind of intermediate value. Therefore, if the current has jumped from 3 amperes to some intermediate value, let us say IL1 0 plus, and this current has jumped from 0 to IL2 0 plus, both being equal to each other, and let us call this simply I0 plus. Then there must be the voltage across this inductor VL1 and the voltage across the inductor VL2, let us say VL2 like this. They must have some kind of sudden jumps in current, therefore, there must be an impulses present in this voltage as well as this voltage. So, the impulse in VL1, if from t equals 0 minus to t equals 0 plus, in this range, in this small range, elementary range, in the jump from 0 minus to 0 plus, the voltage across inductance L1 must be described as L1 times current has jumped from 3 amperes to IL1 0 plus. So, IL1 0 plus, which is simply I0 plus, we write I0 plus minus original current was 3 amperes. So, that is the strength of the impulse. So, there must be an impulse voltage which is equal to L1 times I0 plus minus 3 times delta t, because suddenly this current has jumped from this to this. So, it is negative impulse. As a matter of fact, if I0 plus is smaller than 3, this is a negative impulse, and VL2 is L2 times I0 plus minus the original current, which is 0, times delta t. So, the current in this inductor has jumped from 0 to IL2 0 plus, which is I0 plus, which we call I0 plus. So, other voltages in this circuit are finite, this is finite, the currents are finite, therefore the resistance drops are also finite. Therefore, this impulse voltage must be matched by this impulse voltage, so that Kirchhoff's voltage law is satisfied. To satisfy Kirchhoff's voltage law, we require therefore that these two impulses must be matched. So, L1 I0 plus minus 3 plus L2 times I0 plus minus 0, this must be equal to 0, because the strength of this impulse plus the strength of this impulse, VL1 plus VL2 must be equal to 0, the two impulses must add up to 0. So, solving this, we get that L1 plus L2 times I0 plus equals L1 times 3, L1 equals 2 Henries, therefore this is 6, therefore I0 plus equals 6 divided by L1 plus L2, which is 3, that is 2 amperes. Therefore, this current has jumped from 3 amperes to 2 amperes, and this current has jumped from 0 to 2 amperes. Now, this particular equation that we have here is the one that now fixes the new value of the current, and this is usually referred to as constant flux linkage theorem. Constant flux linkage principle. What it means is L1 plus L2 times I0 plus is the flux linkage associated with the circuit, the total inductance times the current passing through that, and this is the initial flux linkage in the circuit, because L2 does not carry any current. This is the flux linkage associated with L1. So, flux linkages in a circuit which do not have any net impulse EMF in the circuit cannot change suddenly. The result is that the old flux linkages must be equal to the new flux linkages, and therefore that fixes the new value of the current. This is another way of looking at it. In any case, what we want to demonstrate to this example is that there may be cases where inductor currents can be discontinuous, and such cases arise whenever, as a result of a switching operation, a new restriction on the inductor currents is brought into effect or brought into force where previously none existed. Therefore, whatever currents which they were having at t equals 0 minus will no longer satisfy Kirchhoff's current law in the new regime. Therefore, one or more of the currents have to jump, and that can be resolved using principles like this, trying to match the impulse voltages that arise, or using the principle of constant flux linkages. Remember that the why we said in the first, why we normally say inductor current is continuous in the elementary treatment is because we say if the inductor current had jumped, there must be an impulse voltage, infinite voltage across the inductor. Since all other voltages are finite, this infinite voltage cannot exist, therefore inductor current must be continuous. But in situations like this, no doubt an impulse voltage arises across an inductor, but that is matched by another impulse voltage across a second inductor or a third inductor, as the case may be, and the whole Kirchhoff's current law can be satisfied only if such impulse voltages exist. Therefore, this is a particular case which one has to keep in mind whenever you, as a result of a switching operation, a new constraint on inductor currents is brought about. Just as inductor currents can be discontinuous in special cases, and we have to calculate the t equals 0 plus values given the t equals 0 minus values using techniques as we have seen in the last example. A similar situation arises in special cases where the capacitor voltages at t equals 0 minus need not be the same at the values at t equals 0 plus. Let us consider this example. Let us imagine that switch is kept open for a long time till all the voltages get stabilized, and let us assume that the C2 is also initially not charged, in which case the voltage across this capacitor becomes 1 volt because this 2 volts gets divided across the two 1 ohm resistances, therefore Vc1 will become 1 volt, whereas this becomes 2 volts, this is 2 volt, this is 1 volt, and this is 0 volts. But once you close the switch, these three capacitors form a loop, therefore all the three voltages must add up to 0, and if this is 2 volts and this is 1 volt and this is 0 volts, there is no way in which all the 3 voltages are going to add up to 0. Therefore, something must give in, and what happens is all the voltages of the capacitors change to satisfy Kirchhoff's voltage law, and therefore the voltages of the capacitors can be discontinuous. Let us see how we go about it. At t equals 0 minus, we are interested only in the capacitor voltages, because all the other voltages, all the other elements carry finite currents, and because of the jump in capacitor voltages, infinite currents or impulse currents must flow through the capacitors, and therefore we are taking stock of only the impulse currents in this transition. Therefore, all other element currents are finite, we can disregard them. So we have this C3, I will call that Vc3 0 minus, which is 2 volts, and there is a switch, of course, and this I will say Vc2 0 minus, that is of course 0, and then you have this capacitor C1 Vc1 0 minus, that happens to be 1 volt. So that is the situation at t equals 0 minus, and because the switch is open, there is no necessity for all the 3 voltages to add up to 0, because the balance residual voltage is absorbed by the switch. Now at t equals 0 plus, you have again the switch is closed, therefore these 3 capacitors form a loop. Vc1 0 plus, and let us say this is Vc2, sorry, this is the reference sign we have taken, yes, Vc2 0 plus, and this is Vc3 0 plus. So we have a new regime at t equals 0 plus, Vc3 0 plus, Vc2 0 plus, and Vc1 0 plus. Kirchhoff's voltage law tells us Vc3 0 plus equals Vc1 0 plus plus Vc2 0 plus. Right. So, but what is Vc3 0 minus 2 volts? Vc3 0 plus maybe not be 2 volts. So there must be some initial instantaneous change of capacitor voltage. That means in the process between t equals 0 minus to 0 plus, a charge q must flow through these 3 capacitors. This q is the charge flow through the loop in the interval t equals 0 minus to t equals 0 plus. So there must be a sudden increase or decrease in charge in the capacitors. That means impulse current must flow, dq by dt will turn out by impulse, that the current is impulse, but the area under the impulse is finite, therefore instantaneously an additional charge must flow. And what is the value of this charge? Vc3 0 plus equals Vc3 0 minus, this is Vc3 0 minus, and there is a charge q is coming out, therefore the resulting voltage drop is q by C3, Vc3 0 minus minus q by C3, because there is some charge. When q comes out, it is getting discharged, and the amount of discharge represents a voltage drop of q minus C3. So Vc3 0 plus is Vc3 0 minus divided by minus q by C3, and Vc1 0 plus is equal to Vc1 0 minus plus q divided by C1. Some additional charge is put on this capacitor, and similarly Vc2 0 minus plus q upon C. And this q is a common charge which flows to this loop. That means there is an impulse current which integrated over the interval from 0 minus to 0 plus represents a non-zero amount of charge. And in this equation, we know Vc3 0 minus, Vc1 0 minus, and Vc2 0 minus. You can calculate q using the numerical values, and that turns out to be, if you solve this, you will have, let me write this down here, q times 1 over C1 plus 1 over C2 plus 1 over C3. Solving this equation, you will get this as 1. That is the unbalanced voltages that you get here, and from this you get Q equals 6 by 11 coulombs, and therefore you have Vc30 plus, you can calculate using this, it becomes 20 upon 11 volts, and Vc20 0 plus equals 3 upon 11 volts, and Vc10 plus will be 17 upon 11 volts. So the capacitor voltage is indeed has jumped, and this represents an impulse current of 6 upon 11 delta T. This is the description of the current in the interval t equals 0 minus to t equals 0 plus. All the components of the currents which are finite we have ignored. So this example illustrates a situation where the capacitor voltages have to change, and therefore when you want to solve for the transient analysis of this problem, if you know the capacitor voltage at t equals 0 minus, and for the solution of the differential equations you need to know the initial conditions at t equals 0 plus, you have to calculate these values. This points out, of course, one of the difficulties in the classical method of solution of differential equations. From t equals 0 minus, you have to calculate the t equals 0 plus conditions, not only for various response quantities, but even for reactive elements. Sometimes you may have to calculate these values using principles of that, like this. What we have really assumed here is that as far as the capacitors are concerned, the charge is conserved. Whatever is discharged here, it goes to charge these two. Therefore this is just like the principle of conservation of flux linkages as applicable to inductors is what we discussed earlier. This is the principle of conservation of charge across the capacitors. So we will leave this discussion at this stage. I mean, all my intention is to point out that in the calculation of initial conditions you have problems in the classical differential equation approach, not only to calculate the initial conditions and the various initial values, the various derivatives of the response quantities, but even for reactive elements themselves, it may or may not be continuous depending upon the special situation that we have on hand. Let us now introduce ourselves to the concept of characteristic signal of a linear system and the concept of system function. We will consider a linear time invariant constant parameter, that is time invariant or constant parameter mean one and the same, continuous time system. So linear constant parameter continuous time system. We have an input quantity x of t and an output quantity y of t. An electrical network consisting of RLC elements being a specific example of this. In general, the output yt and the input xt are connected by a linear differential equation with constant coefficients. Let us assume that the differential equation connecting these two is of this form: an dny dtn plus an minus 1 dn minus 1 y dtn minus 1, and so on and so forth, plus a naught y equals dm x dtm plus bm minus 1, you can put bm if you like, bm minus 1 dm minus 1 x dtm minus 1, so on and so forth, plus b naught x. So this is a nth order differential equation connecting the output quantity y with the input quantity x. Now the particular integral solution of this is given by the operator bm dm plus bm minus 1 dm minus 1 down the line to b naught divided by an dn plus an minus 1 dn minus 1, so on, plus a naught. This is a operator, a function of d operating on x of t. So, depending upon the input quantity, you can calculate the particular integral solution for this. This is what we do in the case of solution of the differential equations. And the electrical network which we considered in the last lecture is a specific example. You remember that we ended up with a second order differential equation from which we can calculate the particular integral solution in the same manner as here. Now, it turns out that if the input function is of a particular type, exponential function a e to the power of st, then the particular integral solution is this operator operating on a e to the power of st. And from the theory of differential equations, whenever you have an exponential function here, this operator function can be thought of as an algebraic function where d is replaced by a particular value of s. So, it turns out that the particular integral solution will be bm s to the power of m plus bm minus 1 s to the power of m minus 1 down the line to b naught divided by an s to the power of n an minus 1 s to the power of n minus 1 up to a naught times x of t, which is a e to the power of st. So, the solution for this differential equation, the particular integral solution, all you have to do is substitute s for d. So, if x is a e to the power of st, ypi is some quantity times a e to the power of st. We often call this hfs, a e to the power of st. So, the particular integral solution, a function of time, is hs times a e to the power of st or hs times xt, when xt equals a e to the power of st. So, this is a very interesting property that the time function describing the first part of the solution and the excitation have got the same function of time, except that it is multiplied by hfs, which is independent of time. So, we can think of this as a proportionality factor. This is a function of only s, but not a function of time. So, the input time function and the output time function as for the particular integral solution are concerned, they are exactly the same, except that it is scaled down by a factor or scaled up by a factor hfs. So, where the input excitation function and the output function have the same form of time function, it is said to be a characteristic signal of a system. The characteristic signal are sometimes called eigen system, eigen function, characteristic function or characteristic signal, also called eigen signal. Again, the meaning of an eigen signal or characteristic signal is, it is that particular signal which, if it is given as input, the output will also have the same time variation except for a scale factor, and that scale factor is hfs in this case. So, e to the power of st is a characteristic signal, e to the power of st with a constant multiplier, any constant, is a characteristic signal of linear time invariant continuous time systems. This is a very important property. Any linear time invariant continuous time system will have this as characteristic signal, and therefore, if the input is in that form, the output is obtained by merely multiplying this by hfs, where hfs is a kind of proportionality factor. And this hfs is called the system function. And in describing the characteristic signal, s can be complex, s need not be real, it can be need not be imagined, it can be complex in general. Therefore, a complex exponential signal of this type, a e to the power of st, mathematically a can be complex as well. Therefore, a e to the power of st is a characteristic signal, and the complex frequency associated with this signal is s. And the system function, which represents the proportionality constant between the output and the input, is called the system function. It is a function of the complex frequency of the characteristic signal e to the power of st. This is called a system function, and this will be the form Bm s to the power of m plus b naught divided by an s to the power of n down the line to a naught. So, if you know the differential equation, then the system function can be easily be obtained. After all, you have got Bm s to the power of m, Bm minus 1, the same coefficients appear in the two polynomials constituting the rational function HFS. So, this system function is a rational function for lumped parameter systems which we are dealing with. Rational function means it is a ratio of two polynomials, and for linear lumped parameter systems, system function turns out to be a rational function, is a ratio of two polynomials. If I call this g of s over f of s, g and s are two polynomials, and these two polynomials are easily set up. If you look at the differential equations, the coefficients in the differential equation constitute the constants in these two polynomials. So, and further, it is, since it is a rational function of a complex frequency variable s, two polynomials, we also would find it useful to represent this in this manner, some constant m times s minus z1, s minus z2, so on. Since this is an mth order polynomial, you have s minus zm divided by s minus p1, s minus p2, and so on, s minus pn. So, you can factorize the numerator and denominator in this form, and the set of values are called the zeros of f. HFS. These are the values of s which make HFS 0, go to 0. If s is equal to z1 or z2 or whatever it is, the HFS becomes 0. That is why they are called the zeros of HFS. The set of values of p which make the denominator vanish are called poles of HFS. These are terms which some of you may be familiar with from your study of complex variable theory. So, in any case, at the frequencies of s, at s values of s which correspond to a pole of HFS, HFS becomes infinitely large, it blows up. That means the denominator is made equal to 0. On the other hand, if s equal to zi, any I equals 1 to m, then the system function becomes 0. These are usually represented in the complex plane by the 0 locations are given like this, and the pole locations are given by crosses. So, these represent poles, and the zeros are represented by small zeros. Since these are values are in general are complex, then they can be represented in the complex plane. This is called the S plane or complex plane, and the values of the zeros and poles are represented in this fashion. And you recall that whenever these coefficients are all real, whenever there is a complex pole, it is accompanied by its conjugate. Whenever there is a complex zero, it is accompanied by its conjugate. So, they appear in pairs. Of course, as far as real zeros and real poles are concerned, they can appear of unit order singly without any second pole or zero appearing as a conjugate, because the zero or pole is itself by itself real. There is no necessity for a conjugate pole or zero to appear, since they are real. Now, system function plays a very important role in linear system studies, as we will see later, and particularly when you take up Laplace transform techniques. This system function is a very important tool in our analysis of linear systems. But it has nothing to do with Laplace transforms really. It is we can regard this as the ratio of the forced response to the excitation when the excitation is of the form a e to the power of st. That is all we need to know about it. So, what we have seen now is that if we are talking about a linear time invariant continuous time system represented by this black box with an output and an input xt and yt, then the forced response of the system, instead of particular integral solution, I am calling YFS, that is forced response, is HFS times xt, if xt is a characteristic signal. This is the summary of what we have discussed just now. This proportionality is valid only when xt is of the form a to the power of st, not for other signals. That is important. And secondly, we saw that h of s is the ratio of two polynomials in S, g of s over f of s. And if you look at the way in which we calculated g of s and f of s, we took the operator function giving the particular integral solution and formed f of s and g of s. F of s equals a n s to the power of n, a n minus 1 s to the power of n minus 1, and so on and so forth. So f of s equal to 0 is the characteristic equation. That is the characteristic equation from the differential equation. That is what is called the auxiliary equation. So the zeros of roots of this equation which are the same as poles of h of s. We said poles of h of s are the zeros of f of s, are the roots of the equation f of s equals 0. So the roots of f of s equals 0, that equation, which are can be called also zeros of f of s. The roots of the equation f s equals 0 can be termed as zeros of f of s, values of s which makes f of s 0, which are also the poles of h of s. These are give the natural frequencies of the system. What is meant by natural frequencies? These are the frequencies present in the complementary solution or the homogeneous differential equation solution. So this h of s builds in itself a lot of properties. Not only it gives the forced response for this type of excitation, but it also gives you the form of the complementary solution straight away. So whatever information is available in the differential equation is built in this system function. Once you have the system function, you do not have to look at the differential equation again, because all the information that is available in the differential equation is given here, because from this you can set up the differential equation if you wish. Now, but you do not even have to do it, because the complementary solution, if you want, all you have to do is solve for f of s equal to 0, that equation. It gives you all the terms that are present in the natural part of the solution or the complementary solution. In special cases, it often turns out that we would like to have xt of the form e to the power of j omega t. This is a special case of xt being e to the power of st. If xt is e to the power of j omega t, that means we are taking s equals j omega, in which case the forced response will be h instead of s, it is j omega times x of t, where xt is e to the power. Now this is important because whenever we are talking about sinusoidal quantities as the excitations or inputs, sin omega t, cos omega t, they can be related to the e to the power of j omega t. For example, cos omega t can be thought of as the real part of e to the power of j omega t. Alternately, you can think of this as the sum of two exponential functions, as I already mentioned earlier. Similarly, sin omega t can be regarded as the imaginary part of e to the power of j omega t, or the combination of two characteristic signals like this. So e to the power of j omega t is closely related to the sinusoidal functions, which are very important in system studies, and therefore the response of a system to the signal of e to the power of j omega t can be regarded as a special case of the response to an exponential signal e to the power of st. After all, e to the power of st and e to the power of j omega t are closely related. So this is also important, and when we study later on Fourier transform methods and Fourier series methods, h of j omega becomes very important, and This h of j omega is itself sometimes called system function, but more commonly we can call it the frequency response function. Frequency response function. Also sometimes when there is no scope for confusion, this is also called system function. So this is very important, that is h of j omega is also regarded as system function or a frequency response function. This is a special case of h of s when s is equal to j omega, and this becomes very important when we analyze any system on the basis of sinusoidal inputs, because e to the power of j omega is as good as cos omega t or sin omega t as far as analysis is concerned. We then before we move on to other topics, let us see what kind of system function you have when we have discrete time systems. As an example, let us take a second order discrete time system. B naught xn. Now this is a second order discrete time linear constant parameter discrete time system. What we have studied earlier is a continuous time system, this is a discrete time system. It can be shown that xn equals some constant times Zn is a characteristic signal. So just like e to the power of st being a characteristic signal for this continuous time domain, in the case of discrete time system, a to the power of a times z to the power of n is a characteristic signal. A is a multiplying constant, we can disregard that. Z to the power of n is a characteristic signal, and the forced response yn, the particular integral solution for yn, can be written as b2z squared plus b1z plus b naught divided by a2z squared plus a1z plus a naught multiplied by x of n, when x of n is a characteristic signal. So if x of n is a characteristic signal, the forced response of the second order discrete time signal will be b2z squared plus b1z plus b naught by a2z squared plus a1z plus a naught, just in the same way as we had in the continuous case. From these coefficients you form these two polynomials, and this we will write this h of z, where h of z is, of course, once again xn is a characteristic signal, is to the power of n, and h of z is called again system function in this case. So this is a discrete time system function which is a function of z, h of z, just like h of s you have got h of z here, and the working is quite analogous to the continuous time case. The characteristic signal is z to the power of n instead of e to the power of st, and the system function is h of z instead of h of s, but z is the polynomial, z is the variable that you get in this. We will deal with this later at the end of the course when we deal with discrete time systems. So this is a parallel development as applicable to discrete time systems. It completely follows the same lines that we have for the continuous time system. So far we have talked about three different ways of characterizing a linear system. What are the different ways? Let us see what they are. So far we have discussed different ways of dealing with linear systems. Let us see what they are, recapitulate what they are. One is the differential equations. Solution of the differential equations will give us the transient solution. We saw the difficulties associated with this. Second method is system function HFS. You can use the system function, it gives the same information as the differential equation, HFS. Then we also saw an equivalent is the frequency response function. HFJ omega. It turns out that when we later on study Laplace transformation methods, the system function comes into its own. We will try to exploit the properties of the system function to deal with the transients. And when we study later the Fourier transform methods, we will use the frequency response function HFJ omega. There is also a fourth way of describing the system response. This is called the impulse response. So if you give an impulse to a system, the input is an impulse, the output we call it impulse response, unit impulse, this HFT. This is an independent way of characterizing a system. All are equivalent. That is, if you know the system function HFS, you will be able to analyze find out the response for any given excitation. Similarly, if you know frequency response function HFJ omega, you should be able to find out the response to any excitation. And likewise, an impulse response HFT is also an independent way of characterizing a linear system. If you know the response to an impulse, you should be able to find out the response to any given input x of t. And that is also an independent way of doing this. There is yet another way, what is called the step response. So here you are giving u of t, unit step as the input, and what you get is the output at, that is the step response. These are all different ways of characterizing a linear system, and all are equivalent. Each will give complete information about the system which you need to solve for the response under any given excitation. We have studied the differential equation to some extent, and we will leave it at that. We have noted the methodology that is involved, and we also noted some of the difficulties. The difficulties will be overcome when you use the system function approach using the Laplace transformation methods, which we will take up at some later point in this course. And we will also study how to exploit the information that is available in h of j omega, the frequency response function, when we study Fourier series and Fourier integral methods. But we do not have to go to this complex frequency or the frequency omega. We can carry out the work in time domain using the impulse response or the step response. They are independent ways of characterizing the input output relations of a linear system, and this is something which we will look up, we will examine in some detail in the next lecture. But we will use this information again further when we go to Laplace transformation methods. We will see how the HFS system function and the impulse response h of t, how they are closely related to each other. That will be taken up at a later point of time. But in the next lecture, we would have a closer look at the impulse response method of characterizing a linear system.